When you look up at the night sky on a clear evening, away from city lights, you see thousands of stars scattered across the darkness. Each one is a sun, many larger than our own, and between them lie distances so vast that light itself takes years to cross the gaps. You might see the pale band of the Milky Way stretching overhead, that river of ancient light composed of hundreds of billions of stars too distant to resolve individually. You might catch Jupiter's steady gleam, or the red spark of Mars, or, if you're lucky, the smudge of the Andromeda galaxy, 2.5 million light-years away. What you're seeing is already extraordinary. But here's something even more remarkable. Everything you can see with your eyes, everything humanity has ever observed with our most powerful telescopes, every galaxy and star and wisp of cosmic gas we've ever detected, all of it exists within an invisible boundary, a horizon, a limit. Beyond this edge lies more universe, perhaps infinitely more, but it's a universe we cannot see, cannot measure, cannot ever reach. The cosmos itself has drawn a circle around us, and that circle defines the limits of what we can know about reality. This isn't a technological limitation. We're not talking about waiting for better telescopes or more sensitive instruments. The boundary is written into the fundamental structure of space-time itself. It's carved by the speed of light, shaped by the age of the universe, and constantly being redrawn by the expansion of space. No matter how advanced our technology becomes, no matter how long our civilization endures, there will always be parts of the universe that remain forever beyond our reach, forever unseen, forever unknown. Tonight, we're going to explore these boundaries. We'll journey to the edge of the observable universe and peer at the horizons that define what human beings can and cannot know about the cosmos. We'll encounter not one horizon, but several, each one marking a different kind of limit, each one revealing something profound about the nature of space, time, and observation itself. We'll discover why the observable universe is so much larger than you might expect, why some things we can see we can never reach, and what lies beyond the edge of everything we can observe. We'll explore how the universe is slowly hiding itself from us, drawing its curtains closed as space itself expands, and what this means for the distant future of cosmic observation. These horizons aren't just astronomical curiosities, they're boundaries of knowledge itself. They force us to confront questions about the difference between what's unknown and what's unknowable, between temporary ignorance and permanent mystery. They remind us that science, for all its power, operates within limits, and that some of the most profound questions we can ask might not have answers we can ever verify. So settle in as we travel to the edge of everything humans can observe. Let's explore the cosmic cage made of light and time and consider what it means to live inside an island of knowledge surrounded by an ocean of the forever unseen. Let's start with a question that seems simple but opens up into something much stranger. If you asked someone on the street, they might give you an answer that sounds reasonable. The universe is about 13.8 billion years old, they might say, having heard that number from documentaries or articles. Light travels at a fixed speed about 300,000 kilometers per second. So, the farthest thing we could possibly see would be something whose light has been traveling toward us since the beginning of time. That would put it about 13.8 billion light-years away. The observable universe, then, would be a sphere with a radius of 13.8 billion light-years centered on Earth. This answer is logical, it's intuitive, and it's wrong. The radius of the observable universe is not 13.8 billion light-years. It's approximately 46.5 billion light-years. The observable universe is a sphere nearly 93 billion light-years in diameter. This means the most distant objects we can observe are now, at this moment, roughly 46.5 billion light-years away from us, more than 3 times farther than that simple calculation would suggest. How can this be? How can we see objects that are 46.5 billion light years away if the universe is only 13.8 billion years old? The answer reveals something fundamental about what observable really means, and it requires us to understand that space itself is not a static stage on which events unfold. Space itself is expanding, stretching, growing larger with every passing moment. Here's what actually happens. Imagine a photon, a particle of light that was emitted from some distant galaxy a very long time ago, let's say when the universe was young. At that moment, the galaxy might have been, say, a few 100 million light years away from the point in space that would eventually become Earth. The photon begins its journey toward us, traveling at the speed of light, always at the same velocity, never speeding up or slowing down. But as that photon travels through space, the space itself is expanding. The distance between the photon's starting point and its destination is growing. It's as if the photon is trying to cross a river, but the river is getting wider as it swims. From the photon's perspective, if photons had perspectives, it's making progress, always moving at the speed of light. But from our perspective, the journey takes longer than we might expect because the destination keeps receding. Eventually, after billions of years of travel, that photon reaches us. We detect it. We observe the galaxy it came from. But during those billions of years, while the photon was in transit, the universe continued expanding. The galaxy that emitted the photon has been carried away by the expansion of space. So while the photon was emitted by a galaxy that was, perhaps, a billion light years away at the time of emission, by the time we receive that photon, the galaxy itself has receded to a much greater distance, perhaps 30 or 40 billion light years away. This is why the observable universe is so much larger than 13.8 billion light years. We're not just seeing how far light could travel in 13.8 billion years through static space. We're seeing how far light could travel while space itself was expanding, stretching, growing. The proper distance, the distance you would measure if you could freeze the expansion of the universe right now and stretch a measuring tape from here to there, is much greater than the light travel distance. This expansion is described by something called the scale factor, a mathematical quantity that tells us how much space has stretched since some reference time. When we look at distant galaxies, we're seeing them as they were in the past, when the universe was smaller and denser. The cosmic microwave background radiation, the most distant light we can observe, was emitted when the universe was only 380,000 years old. At that time, the matter that emitted that radiation was only about 42 million light years away from the point that would become our location. But in the 13.8 billion years since then, the universe has expanded by a factor of about 1,100. That matter is now approximately 46 billion light years away from us. Think about it like this. Imagine baking bread with raisins in it. Before you put the dough in the oven, you mark 2 raisins that are 1 centimeter apart. As the dough rises, the raisins move away from each other, not because they're traveling through the dough, but because the dough itself is expanding. By the time the bread is fully risen, those 2 raisins might be 3 centimeters apart. Neither raisin moved through the dough more than a tiny amount. The space between them simply grew. The universe works the same way. Galaxies aren't, mostly, moving through space. Space itself is expanding, carrying galaxies along with it. This has a profound consequence. The distance to an object we observe is greater than the light travel time would suggest, because the space between us and that object has been stretching while the light was traveling toward us. Now, here's where it gets even more interesting. The observable universe is not the same as the entire universe. When astronomers say the observable universe, they mean specifically the region of space from which light has had time to reach us since the beginning of the universe. It's defined by our past, by the finite age of the cosmos, and by the speed of light. But the actual universe, the total universe, could be much, much larger than the observable portion. It could even be infinite. No evidence suggests that the observable universe has any special status. We don't sit at the center of all existence. We sit at the center of our own observable bubble, but every point in space has its own observable universe centered on it. An observer in a galaxy 50 billion light-years from us would have their own observable sphere, which would overlap with ours but also extend into regions we can never see. And an observer in a galaxy even farther away, beyond our cosmic horizon, would inhabit an observable universe that doesn't overlap with ours at all. They could never see us, and we could never see them, even in principle. This is what observable really means. It's not about the quality of our telescopes or the sensitivity of our detectors. It's about the fundamental structure of space-time. There is a sphere around us, roughly 46.5 billion light-years in radius, and this sphere contains everything we can possibly observe. Beyond this boundary, light has not had enough time to reach us yet. The universe might extend infinitely in all directions, filled with countless galaxies and stars and worlds. But if it's beyond our horizon, it's beyond our knowledge. Edwin Hubble, working at Mount Wilson Observatory in the 1920 seconds, was the first to demonstrate that the universe is expanding. He observed distant galaxies and noticed that their light was shifted toward the red end of the spectrum, red-shifted, indicating they were moving away from us. Moreover, he found that the farther away a galaxy was, the faster it appeared to be receding. This relationship, now known as Hubble's law, revealed that space itself was expanding uniformly in all directions. Later, astronomers refined these measurements and discovered something even more startling. The expansion isn't slowing down, as gravity would suggest. It's speeding up. In 1998, two teams of astronomers studying distant supernovae discovered that the universe's expansion is accelerating. This discovery, which would earn Saul Perlmutter, Brian Schmidt, and Adam Rees the Nobel Prize in Physics in 2011, showed that something, an unknown influence they called dark energy, is pushing the universe to expand faster and faster. This acceleration has profound implications for the limits of observation. It means the observable universe, while currently about 93 billion light-years in diameter, will eventually stop growing in a certain sense. Even though time continues to pass, and even though light from farther regions continues to arrive, the accelerating expansion will eventually carry distant regions away from us, faster than light can cross the growing gulf between us. Galaxies that are currently visible will, over vast timescales, recede beyond our cosmic horizon and disappear from view. It's pulling itself apart, hiding itself from observation, but we're getting ahead of ourselves. Before we can understand what happens at the edge of the observable universe, we need to understand the different types of horizons that exist. And there are several, each marking a different kind of boundary, each revealing something different about the limits of what we can know. The first and most fundamental is called the particle horizon. The particle horizon is, in many ways, the most intuitive of the cosmic horizons. It's the answer to a simple question: what is the maximum distance from which light could have traveled to reach us in the age of the universe? At first glance, this seems like it should be straightforward. The universe is 13.8 billion years old. Light travels at 300,000 kilometers per second. So, the particle horizon should be 13.8 billion light years away, right? But, as we've already seen, the expansion of space complicates this picture. The particle horizon is actually much farther away, about 46.5 billion light years. To understand the particle horizon, we need to think about causality. The particle horizon marks the boundary of what could have causally influenced us. Any event that occurred inside our particle horizon could, in principle, have sent us a signal. Any event outside our particle horizon could not have affected us yet, because not enough time has passed for light or any signal to cross the distance. This horizon is called the particle horizon because it's defined by particles, specifically by the light particles, photons, that could have reached us. It's also sometimes called the cosmological horizon or the co-moving horizon. The word co-moving refers to a coordinate system that expands with the universe itself, a mathematical tool that helps cosmologists account for the expansion of space. The particle horizon grows with time. As the universe gets older, light from more distant regions has time to reach us, and our observable universe expands. Every moment that passes, every second that ticks by, the particle horizon recedes a little farther into the distance. We see a tiny bit more of the universe. New regions of space, previously beyond our observational reach, cross the threshold and become visible. But here's where it gets subtle. The particle horizon grows, but it doesn't grow at the speed of light. In fact, it grows faster than the speed of light, not because anything is moving faster than light, but because space itself is expanding everywhere at once. This sounds paradoxical. How can a horizon defined by light move faster than light itself? The answer lies in the expansion of space. Imagine you're standing at the center of an enormous field, and every second, the field doubles in size. You can see a certain distance. Let's say you can see anything within 100 meters of you. As the field expands, carrying everything with it, objects that were once at the edge of your visibility get carried farther away. But because the expansion is happening everywhere at once, new regions that were previously beyond your sight get carried into view. Your visible horizon is receding, but not because you're moving or because light is traveling faster. It's because the space itself is expanding, bringing new regions into causal contact with you. In our universe, the particle horizon is currently receding at about 3.2 times the speed of light. This doesn't violate relativity. No object is moving through space faster than light, but space itself is expanding, and there's no speed limit on that expansion. The physicist Wolfgang Rindler, working in the 1950 seconds, was instrumental in clarifying the concept of cosmological horizons. He made a crucial distinction between instantaneous events, like a supernova explosion, and world lines, the paths that objects trace through space-time as they endure over time. This distinction helped cosmologists understand what it means for something to be observable and how horizons function in an expanding universe. Rindler showed that in a universe described by general relativity and the Friedmann equations, the mathematical framework that describes how the universe expands, there exists a well-defined particle horizon. This horizon depends on the history of the universe's expansion. If the universe expanded very rapidly in its early moments, which, as we'll discuss later, seems to be exactly what happened, then the particle horizon is pushed farther out. If the universe expanded more slowly, the horizon would be closer. The particle horizon is what defines the size of the observable universe. Everything inside the particle horizon is, at least in principle, observable. Everything outside it is not yet. Given enough time, some of those regions outside our current particle horizon will cross the threshold and become observable. But, crucially, not all of them will. And this brings us to a second, more troubling kind of horizon. Before we get to that, though, we need to understand an important practical limit that sits well inside the particle horizon: the surface of last scattering. When we think about observing the distant universe, we might imagine that if we had a powerful enough telescope, we could see all the way back to the Big Bang itself. We could observe the moment of creation, the first instant of space-time. There's a wall in time we cannot see past. a moment before which the universe was opaque to light. This barrier is called the surface of last scattering, and it sits at the boundary of the observable universe in a very practical sense. It's the oldest light we can ever hope to detect. In the very early universe, conditions were extraordinarily different from what we experience today. The universe was hot, unimaginably hot, and dense. Matter existed as a plasma, a state where electrons are stripped from atomic nuclei and float freely. In this plasma, photons, particles of light, couldn't travel very far before they collided with an electron. The universe was opaque, like a thick fog. Light couldn't stream freely through space. It scattered constantly, bouncing from particle to particle. As the universe expanded, it cooled. About 380,000 years after the Big Bang, when the universe had cooled to a temperature of about 3,000 degrees Kelvin, something remarkable happened. Electrons and protons, which had been flying around freely, began to combine to form neutral hydrogen atoms. This process is called recombination. Though the name is a bit misleading, since the particles were combining for the first time, not recombining. When recombination occurred, the universe suddenly became transparent. And those first free-streaming photons have been traveling through the universe ever since. We observe those photons today as the cosmic microwave background radiation, or CMB. This radiation fills all of space, coming at us from every direction. It's the oldest light in the universe, and it reveals what the cosmos looked like when it was only 380,000 years old. The surface of last scattering is the spherical shell in space from which the CMB photons we observe today were emitted. At the moment those photons began their journey, the matter that emitted them was about 42 million light-years away from the point that would eventually become our location. But the universe has expanded enormously since then by a factor of about 1,100. Space has stretched so much that the matter which emitted the CMB is now approximately 46 billion light-years away from us. The temperature of the CMB tells us something profound. Today, we measure the CMB to have a temperature of about 2.7 Kelvin, just a few degrees above absolute zero. This is vastly cooler than the 3,000 Kelvin it had when it was emitted. The difference is due entirely to the expansion of the universe. As space stretched, the wavelength of the photons stretched with it, shifting toward longer, redder, cooler wavelengths. This cosmological redshift has cooled the ancient radiation by a factor of about 1,100, the same factor by which the universe has expanded. When we observe the CMB, we're seeing the universe as it was at the surface of last scattering. We can see temperature fluctuations in the radiation, tiny variations from one patch of sky to another. These fluctuations, typically only about 1 part in 100,000, represent slight differences in density in the early universe. Regions that were slightly less dense appear cooler. These small density variations were the seeds that would eventually grow into the large-scale structure of the universe, the galaxies, clusters, and vast cosmic web we observe today. The surface of last scattering is not perfectly sharp. Recombination didn't happen instantaneously everywhere at once. It took time, perhaps tens of thousands of years, for the universe to transition from opaque to transparent. So the surface is actually a shell with some thickness to it. Current observations suggest the thickness of the last scattering surface is about 19 megaparsecs, or roughly 62 million light-years. This might sound large, but compared to the scale of the observable universe, it's quite thin, less than 0.2% of the distance to the surface. The cosmic microwave background was discovered accidentally in 1964 by Arno Penzias and Robert Wilson, two radio astronomers working at Bell Telephone Laboratories in New Jersey. They were trying to eliminate noise from a sensitive antenna they were using for radio astronomy. They found a persistent, uniform signal coming from all directions in the sky, a faint hiss in the microwave part of the spectrum. At first, they thought it might be interference perhaps from New York City or from pigeon droppings on their antenna. But no matter what they did, they couldn't get rid of it. What Penzias and Wilson had discovered, though they didn't realize it immediately, was the afterglow of the Big Bang. Other physicists, including Robert Dicke and Jim Peebles at Princeton University, had predicted that such radiation should exist. When Penzias and Wilson's discovery was announced, it provided powerful confirmation of the Big Bang theory. For this discovery, Penzias and Wilson were awarded the Nobel Prize in Physics in 1978. Since then, the cosmic microwave background has been studied in exquisite detail by a series of increasingly sophisticated instruments. The COBE satellite in the 1990 seconds mapped the large-scale fluctuations in the CMB. The WMAP satellite in the 2000s provided much higher resolution measurements. And the Planck satellite, launched by the European Space Agency in 2009, has given us the most precise measurements yet, mapping the CMB with extraordinary accuracy. These observations have allowed cosmologists to determine the age, composition, and geometry of the universe with remarkable precision. We know the universe is 13.8 billion years old. We know it's geometrically flat, or very nearly so. We know its composition, about 5% ordinary matter, about 27% dark matter, and about 68% dark energy. All of this information comes from studying the patterns in the cosmic microwave background, but here's the crucial point. We cannot see past the surface of last scattering, everything that happened before the universe became transparent. The first 380,000 years of cosmic history is hidden behind an impenetrable veil. We can infer what happened during that time using physics and mathematics. We can build theoretical models and test their predictions against what we observe in the CMB, but we cannot directly observe that early era with light. This makes the surface of last scattering a practical horizon, different in nature from the particle horizon but no less real as a boundary on observation. No matter how powerful our telescopes become, we will never see light from earlier than 380,000 years after the Big Bang. That light doesn't exist. It was absorbed and scattered in the opaque plasma of the early universe. There are, potentially, other ways to observe the early universe. Neutrinos, ghostly particles that barely interact with matter, could have streamed freely through the early universe, even when it was opaque to photons. If we could detect the cosmic neutrino background, the neutrino equivalent of the CMB, we could see back even earlier, to when the universe was only about 1 second old. Similarly, gravitational waves, ripples in spacetime itself, could carry information from the very earliest moments, perhaps from the era of cosmic inflation. But these observations, if they become possible, will be extraordinarily challenging. For now, and likely for a long time to come, the surface of last scattering remains the practical edge of the directly observable universe. Behind this wall of ancient light lies the first 380,000 years of cosmic history. The moment of the Big Bang itself, the first fractions of a second when the universe was so hot that even protons and neutrons couldn't exist, only a soup of quarks and gluons. The possible era of cosmic inflation, when the universe might have expanded exponentially fast, growing from smaller than an atom to macroscopic size in a tiny fraction of a second. We can theorize about these moments. We can build mathematical models and test their predictions, but we cannot observe them directly. The surface of last scattering stands as a barrier, the oldest light, the edge of direct observation in time. And yet, even this is not the most disturbing kind of horizon. There is another boundary, more permanent and more troubling, that we must confront: the event horizon. The event horizon of the cosmos is perhaps the most philosophically unsettling of all the boundaries we encounter. Unlike the particle horizon, which represents what we have seen and could have seen in the past, the event horizon represents what we could ever see in the future, no matter how long we wait. The cosmic event horizon is currently about 16 billion light-years away. This number might seem strange at first. The event horizon is inside the particle horizon. We can see galaxies that are farther away than the event horizon. In fact, we can see galaxies that are currently about 46 billion light-years away, which is far beyond the event horizon. How can we see things that are beyond the horizon of what we can ever see? The answer lies in the difference between the past and the future, between light that has already reached us and light that will never reach us. The event horizon marks the boundary between regions of space that can still communicate with us in the future and regions that cannot. Any event happening now inside our event horizon, any supernova exploding, any message sent could eventually reach us if we wait long enough. The light or signal would take a very long time to arrive, perhaps trillions of years, but it would arrive. Any event happening now outside our event horizon can never reach us. No signal emitted from beyond that boundary, even if traveling at the speed of light, will ever cross the growing gulf of space to reach our location. This is deeply counterintuitive. We can currently observe galaxies that are beyond our event horizon. We see their ancient light, emitted billions of years ago when those galaxies were younger and closer to us. But if a star in one of those galaxies exploded today, the light from that explosion would race toward us at light speed, but space is expanding so rapidly that the distance between us and that light would grow faster than the light could cross it. The photons would run and run but never reach us, like someone trying to walk up a down escalator that's moving too fast. This is the consequence of the accelerating expansion of the universe. As space expands faster and faster, driven by dark energy, the event horizon does not grow. In fact, in some models, it converges to a fixed, proper distance. But many of those galaxies, perhaps most of them, are already beyond our event horizon. We can see their past, but we are forever cut off from their future. Imagine a ship sailing away from you on a vast ocean. When the ship is close, you can see it clearly. As it sails farther away, it becomes smaller, dimmer, but still visible. With a telescope, you can keep it in view even as it recedes. Now imagine that the ocean itself is expanding, that the distance between you and the ship is growing not just because the ship is sailing, but because the water itself is stretching. At some point, the expansion of the ocean becomes so rapid that even though the ship is visible, even though you can see it in your telescope, you know that any signal the ship sends from this moment forward, any light it flashes, any radio wave it broadcasts, will never reach you. The expansion will carry it away faster than the signal can cross back to you. This is our situation with distant galaxies. We watch them receding into the distance, and we know that we are seeing the last light we will ever receive from them. Any light they emit from now on is lost to us forever. The cosmic event horizon was first rigorously described in the context of cosmological models in the mid-20th century, as physicists developed the mathematical framework for understanding horizons in general relativity. The concept is closely related to the event horizon of a black hole, but the physics is different. A black hole's event horizon is a one-way boundary in spacetime, created by intense gravity. The cosmic event horizon is a boundary created by the expansion of space itself. The current distance to our event horizon, about 16 billion light-years, depends on the model of dark energy we use and on the parameters that describe the universe's expansion. If dark energy behaves like a cosmological constant, a fixed energy density of empty space that doesn't change with time, then the event horizon converges to a specific distance and stays there. If dark energy evolves with time, becoming stronger or weaker, the event horizon's behavior might be different. This strange geometry, where we can see farther than we can reach, where the past is visible but the future is inaccessible, is one of the most profound features of our cosmos. It means that much of what we observe is already lost to us. We are seeing the ghosts of galaxies whose futures we cannot access, whose fates we cannot know, whose influence on us has ended even though their image remains. In practical terms, this means that if you wanted to send a spacecraft to a galaxy beyond our event horizon, you couldn't do it. Even if your spacecraft could travel at the speed of light, it would never reach that galaxy. It exists in a part of the universe that is causally disconnected from our own future. This affects not just travel, but also information. Any civilization in a galaxy beyond our event horizon is cut off from us permanently. We can never exchange messages with them. We can never know what happens to them after their light crosses our event horizon. They are, from our perspective, frozen in the past. We see them as they were, billions of years ago. And that image will be the last information we ever receive from them. The event horizon also has implications for the fate of the universe. As space continues to expand and accelerate, more and more galaxies will cross our event horizon. Galaxies that are currently inside the horizon, galaxies from which we could still receive signals, will eventually recede beyond the boundary. Over hundreds of billions of years, the observable universe will actually shrink in a sense. We'll be able to see more of the past, the particle horizon will continue to grow, but we'll be cut off from more and more of the cosmos's future. Eventually, if the acceleration continues, only our local gravitationally bound structures will remain in causal contact. The Milky Way, the Andromeda Galaxy, and the other galaxies in our local group are held together by gravity, and gravity is strong enough to prevent these galaxies from being pulled apart by the expansion of space. But everything outside the local group, all the distant galaxies, the rich clusters, the vast cosmic web, will recede beyond our event horizon. Observers in the distant future, living in a galaxy in our local group trillions of years from now, will see a very different universe than we do. They will see only nearby galaxies. All the distant galaxies will have faded from view, their light redshifted to undetectability. The evidence for the Big Bang, the evidence for the expansion of the universe, the evidence that there's more to the cosmos than the local group, all of it will be gone, erased by the expansion of space. Those future astronomers, if they exist, will live in an empirically smaller universe than we do, not because the universe has actually shrunk, but because observation itself has limits that change with time. They will see an island of galaxies surrounded by darkness, with no way to know that billions of other galaxies exist beyond the horizon. We are, in a sense, lucky to live when we do. We live at a moment in cosmic history when the universe is observable, when evidence for its origin and structure is still within reach. We can see the cosmic microwave background. We can observe distant galaxies spanning most of cosmic history. We can detect the large-scale structure of the cosmos, but this window is closing. Slowly but inexorably, as the universe continues its accelerating expansion. The discovery that the universe's expansion is accelerating ranks among the most surprising findings in the history of astronomy. When two independent teams of researchers announced their results in 1998, they shocked the scientific community. The universe wasn't just expanding, as Edwin Hubble had shown decades earlier. It was expanding faster and faster, accelerating in a way that seemed to require some unknown force pushing space itself apart. The discovery came from observations of type Ia supernovae, a particular kind of stellar explosion that can be used as a standard candle to measure cosmic distances. Type Ia supernovae occur when a white dwarf star, the dense remnant of a sun-like star, accumulates matter from a companion star until it reaches a critical mass and explodes. Because these explosions happen at roughly the same critical mass, they all release similar amounts of energy and reach similar peak brightnesses. By measuring how bright a type Ia supernova appears from Earth, Astronomers can calculate how far away it is. The Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees, both use this technique to measure distances to supernovae in distant galaxies. They could then compare those distances to the galaxy's redshifts, how much their light had been stretched by the expansion of the universe, to determine how the expansion rate has changed over time. What they found was stunning. The distant supernovae were dimmer than expected, fainter than they should have been if the expansion of the universe were slowing down. This meant the supernovae were farther away than expected, which meant the universe had expanded more than anticipated. The only way to explain the observations was if the expansion of the universe had accelerated at some point in the past few billion years. This acceleration requires energy, a lot of it. To make space itself expand faster and faster, there must be some form of energy that permeates empty space, that doesn't dilute as the universe expands, and that has a repulsive effect rather than an attractive one. Physicists call this hypothetical energy, dark energy, and it appears to make up about 68% of the total energy density of the universe. We don't know what dark energy is. We don't understand its fundamental nature. The simplest explanation is that it's a cosmological constant, a fixed energy density of the vacuum of space itself. This is equivalent to a term that Einstein included in his equations of general relativity, though he later abandoned it. In the cosmological constant picture, every cubic meter of empty space has the same amount of dark energy. And as the universe expands and more space comes into existence, the total amount of dark energy increases. Dark matter, by contrast, dilutes as the universe expands. If you have a certain amount of dark matter in a given volume of space, and that volume doubles, the dark matter density is cut in half. The same is true for ordinary matter and for radiation. But dark energy doesn't dilute. If dark energy is a cosmological constant, its density stays the same even as space expands. In the early universe, matter and radiation were much denser than they are today, and their gravity dominated the dynamics of cosmic expansion. The expansion was decelerating, slowing down over time as gravity worked to pull everything back together. But as the universe expanded and matter diluted, dark energy became more and more important. About 5 to 6 billion years ago, dark energy's repulsive effect began to overcome matter's attractive gravity, and the expansion of the universe started to accelerate. This acceleration has profound effects on the cosmic horizons we've been discussing. It's the reason the event horizon exists at all. In a universe where expansion is decelerating, there would be no event horizon. Given enough time, light from any galaxy, no matter how distant, would eventually reach us. But in an accelerating universe, there is a limit. Galaxies beyond a certain distance are receding so fast that even light, traveling at maximum speed, can never cross the growing gulf to reach us. The Hubble sphere is another related concept worth understanding. The Hubble sphere is the distance at which the recession velocity of space equals the speed of light. Inside the Hubble sphere, galaxies are receding slower than light. Outside the Hubble sphere, galaxies are receding faster than light. Right now, the Hubble sphere is about 14 billion light-years away, smaller than the particle horizon but larger than the event horizon. It might seem paradoxical that we can see galaxies outside the Hubble sphere, galaxies that are receding faster than light. How can light from those galaxies reach us if they're moving away faster than light can travel? The answer is that the light was emitted when those galaxies were inside the Hubble sphere, when they were receding slower than light. That light has been traveling toward us for billions of years, and even though the galaxies have since moved beyond the Hubble sphere, the light they emitted long ago is still making progress toward us. Eventually it reaches us, and we observe those galaxies in our telescopes. But here's the key point. Light emitted by those galaxies today will never reach us. Those galaxies are beyond our event horizon. We see their past, but their future is inaccessible. As the accelerated expansion continues, the future of cosmic observation becomes increasingly isolated. Within the local group, the Milky Way and Andromeda and the smaller galaxies bound to them will eventually merge into a single giant elliptical galaxy. This will take billions of years, but it will happen. Meanwhile, all the other galaxies, the distant spirals and ellipticals, the rich clusters, the vast superclusters spanning hundreds of millions of light years, will recede beyond the cosmic event horizon. Current estimates, assuming dark energy remains constant, suggest that in about 150 billion years, all galaxies outside our local supercluster will have disappeared from view, their light redshifted beyond detectability. The cosmic microwave background will have cooled to temperatures so low that it will be effectively impossible to observe. Any astronomers living in that distant future will look out and see only a single, massive galaxy surrounded by darkness. They will have no evidence for the Big Bang, no evidence for cosmic expansion, no hint that billions of other galaxies exist beyond their horizon. This raises a fascinating question. How much of the universe has already disappeared from our view? We can see galaxies as they were billions of years ago, but some of those galaxies may have already crossed our event horizon. We're seeing their ancient light, but their present selves are already lost to us. We are watching a universe that is slowly erasing itself from observation, pulling its own history into an unreachable distance. It's worth noting that the nature of dark energy remains uncertain, and recent observations have sparked new debates. In 2024 and 2025, data from the Dark Energy Spectroscopic Instrument, or DESI, has raised questions about whether dark energy is truly constant or whether it might be evolving with time. Some researchers, including a team led by Young-Wook Lee at Yonsei University, have even suggested that the universe's expansion might already be entering a decelerating phase. Though this interpretation is controversial and most cosmologists remain skeptical, the debate centers on how we interpret observations of distant supernovae and whether there are systematic effects we haven't fully accounted for. Lee's team argues that there's an age bias in how we analyze supernova data, that supernovae in older stellar populations might appear dimmer than those in younger populations, and that this could affect our conclusions about cosmic acceleration. If this is correct, it would require a major revision of our understanding of dark energy and the universe's fate. However, other researchers have pushed back, arguing that the claimed age bias isn't supported by our understanding of how supernovae form, and that the analysis doesn't properly account for known effects. The Vera C. Rubin Observatory, which began observations in 2024, is expected to provide much more data on distant supernovae and should help settle these questions within the next few years. For now, the consensus view is that dark energy exists, that it's causing the universe to expand at an accelerating rate, and that this acceleration will continue into the future. But the precise nature of dark energy and whether its strength might change with time remains one of the biggest open questions in cosmology. What we can say with confidence is that cosmic expansion, whether accelerating or not, has created boundaries around what we can observe. It has divided the universe into regions that can communicate with us and regions that cannot. It has created horizons that limit not just what we can see now, but what we can ever see, even with infinite patience and perfect instruments. And this leads us to one of the most speculative questions in all of cosmology. If the observable universe is just a small fraction of the total universe, what exists in the unobservable regions? The observable universe, that sphere roughly 93 billion light-years across, centered on Earth, might be just a tiny fraction of the total cosmos. In fact, according to some theories, it might be an infinitesimally small fraction. The universe beyond our cosmic horizon could be vastly, perhaps infinitely, larger than what we can observe. This possibility comes from the theory of cosmic inflation, one of the most important ideas in modern cosmology. Inflation proposes that the universe underwent a period of exponentially rapid expansion in its earliest moments during the first tiny fraction of a second after the Big Bang. In an almost inconceivably brief time, space expanded by an enormous factor, growing from smaller than an atom to macroscopic size. The idea was first proposed by physicist Alan Guth in 1980, while he was working at the Stanford Linear Accelerator Center. Guth was trying to solve several puzzles in cosmology, problems that the standard Big Bang theory couldn't easily explain. Why is the universe so uniform, looking essentially the same in all directions? Why is space geometrically flat, or very nearly so? Why don't we observe magnetic monopoles, exotic particles that some theories predicted should be abundant? Guth realized that a brief period of exponential expansion in the very early universe could solve all these problems at once. If the universe expanded by an enormous factor, it would smooth out any initial irregularities, making the universe appear uniform on large scales. It would flatten the geometry of space, just as inflating a balloon makes its surface appear flatter from the perspective of something very small on that surface. And it would dilute the density of magnetic monopoles to undetectably low levels. The inflationary model has been refined and developed over the decades since Guth's original proposal. Andrei Linde, then at the Lebedev Physical Institute in the Soviet Union, developed a version called chaotic inflation, in which different regions of space inflate by different amounts. Linde showed that inflation doesn't need to start uniformly everywhere. It can begin in a chaotic, irregular state and still produce a universe that looks like ours. The key insight is that inflation is driven by a quantum field called the inflaton field. In regions where this field has a high value, space inflates rapidly. As the field rolls down to a lower energy state, inflation slows and eventually stops, and the energy stored in the inflaton field converts into matter and radiation. This is called reheating, and it marks the beginning of the hot, dense phase we traditionally associate with the Big Bang. But here's where things get really interesting. In the 1,980 seconds, physicists including Paul Steinhardt and Alex Vilenkin realized that if inflation can start in some regions, it can start in other regions too. And once it starts, it tends to continue. Regions that are inflating expand so rapidly that even if inflation ends in some small part of that region, the rest continues to inflate, creating more and more space, which itself can spawn new inflating regions. This process is called eternal inflation, and it has a startling implication. Once inflation begins, it never completely ends. It ends in some places, creating bubble universes like ours, where inflation has stopped and matter and galaxies can form. But the inflating space between these bubbles continues to expand, creating more bubbles, which themselves are embedded in even more inflating space. The process continues forever, creating an infinite number of separate bubble universes, each one potentially with different properties. If eternal inflation is correct, our observable universe would be just one bubble in this vast multiverse. Other bubbles, potentially infinite in number, would exist beyond our cosmic horizon. These bubble universes would be causally disconnected from ours. We could never observe them, visit them, or communicate with them. As far as we're concerned, they might as well not exist, since they can never affect us in any way. Moreover, different bubbles might have different physical properties. In some versions of the theory, particularly those connected to string theory, the fundamental constants of nature, the strength of gravity, the mass of the electron, the charge of the proton could take on different values in different bubbles. The laws of physics as we know them might just be local bylaws, applying only in our bubble while different bubbles operate under different rules. This idea, often called the landscape scenario, is deeply controversial. If we observe something surprising, we can always say, well, that's just the way things are in our particular bubble, replacing explanation with an appeal to randomness and selection effects. Paul Steinhardt, one of the original architects of inflation theory, became one of the multiverse's most vocal critics for precisely this reason. He argues that eternal inflation and the multiverse undermine the scientific method by making the theory unfalsifiable. If we can never observe the other universes, and if anything can happen somewhere in the infinite multiverse, then what does the theory actually predict? There are also technical problems with eternal inflation. In 2014, a paper by Coley and Haslam showed that in some popular models of eternal inflation, space-time would develop singularities points where the mathematics breaks down within a finite time. This suggests that eternal inflation, at least in those models, cannot actually be eternal. More recently, in 2018, Stephen Hawking and Thomas Hertog published a paper offering a different perspective. Using tools from string theory and the holographic principle, they argued that the multiverse might be much more limited than eternal inflation predicts. Their approach suggests a finite number of possible universes, not an infinite zoo of every possibility. If Hawking and Hertog are right, the multiverse becomes more predictive and testable. In their words, potentially allowing us to make and test specific predictions about observable consequences. The question of observability is crucial. If the multiverse is real, can we ever find evidence for it? One possibility is that our bubble universe might have collided with another bubble at some point in the past. Such a collision could potentially leave an imprint in the cosmic microwave background, a particular pattern of hot and cold spots that would be recognizable as a collision signature. Several research groups have searched for these signatures in CMB data from the Planck satellite, but so far, no convincing evidence has been found. Another possibility is that the properties of our universe might give us indirect evidence. If the fundamental constants of nature appear to be fine-tuned to allow for the existence of complex structures and life, one explanation could be that we live in one of the rare bubbles where the constants happen to land in a life-permitting range. This is an application of the anthropic principle. The anthropic argument is also controversial. Others see it as a reasonable inference given our cosmological theories and the apparent fine-tuning of physical constants. For our purposes, what matters is this. If inflation is correct, even in its simplest forms, it implies that the universe is vastly larger than the observable portion. The region we can observe is just a tiny bubble in an enormous, possibly infinite cosmos. Beyond our horizon lies more universe, more space, more galaxies, more stars and planets, and perhaps even more observers wondering about the limits of their own observation. Alan Guth once calculated that if inflation occurred in the way most models suggest, the total size of the universe could be at least 10 to the 23rd power times larger than the observable universe. That's a 1 followed by 23 zeros, a trillion times larger. André Linde, in his lectures on eternal inflation, sometimes uses a provocative thought experiment. He suggests that in an infinite multiverse, anything that's not explicitly forbidden by the laws of physics will happen somewhere, not just once, but infinitely many times. This means there would be infinitely many regions of space identical to our observable universe, down to every atom, every star, every planet. There would be infinitely many Earths, with infinitely many versions of you reading these words right now. This idea stretches credibility, and Linde himself presents it as almost a reductio ad absurdum, a way of showing how strange the implications of eternal inflation become. But if the multiverse is truly infinite, and if quantum fluctuations can produce any initial conditions allowed by physics, then such copies are, in a mathematical sense, inevitable. Most physicists are cautious about these speculations. The multiverse might be real, or it might be an artifact of our current theories that will disappear when we develop better understanding. What we can say is that our best current models of the early universe suggest that the cosmos extends far beyond what we can observe. Whether that extension is finite or infinite, whether it contains multiple bubbles with different laws of physics, or just more of the same, we cannot yet say with confidence. What we do know is that the observable universe is not the whole universe. The limits on observation imposed by the speed of light, the age of the cosmos, and the expansion of space mean that most of reality, possibly almost all of reality, is beyond our ability to detect or measure. We live inside an island of knowledge, surrounded by an ocean of the potentially unknowable. The particle horizon and the event horizon are not the only boundaries that limit cosmic observation. There are other horizons, less famous but no less interesting, that mark different kinds of limits on what we can observe about the universe. The surface of last scattering, which we discussed earlier, is one example. It's an optical horizon in the sense that it marks the farthest distance from which photons' ordinary visible light and infrared and microwave radiation can reach us. But other types of particles and signals have their own horizons. Neutrinos, for instance, interact very weakly with matter. A neutrino can pass through a light year of solid lead with only a 50% chance of interacting with an atom. This means neutrinos became free-streaming, able to travel through the universe without scattering much earlier than photons did. While photons were still bouncing around in the opaque plasma of the early universe, neutrinos were already traveling freely through space. This suggests the existence of a cosmic neutrino background, analogous to the cosmic microwave background but consisting of neutrinos rather than photons. These relic neutrinos were produced in the first few seconds after the Big Bang, when the universe was hot enough for neutrinos to be in thermal equilibrium with other particles. As the universe expanded and cooled, the neutrinos decoupled from matter and began free streaming. They've been traveling through space ever since, and they should fill the universe with a background of low-energy neutrinos. If we could detect the cosmic neutrino background, a tremendous technological challenge given how weakly neutrinos interact, we would be able to probe the universe as it was when it was only about 1 second old. This is much earlier than the surface of last scattering, which shows us the universe at 380,000 years old. The neutrino horizon extends farther back in time than the photon horizon, giving us a window into even earlier cosmic history. Similarly, gravitational waves ripples in the fabric of spacetime itself could potentially allow us to probe even earlier moments. Gravitational waves interact even more weakly with matter than neutrinos do. They essentially don't interact at all, passing through matter as if it weren't there. This means gravitational waves produced in the very early universe, perhaps during the era of cosmic inflation itself, could still be traveling through the cosmos, carrying information about conditions in the first tiny fraction of a second after the Big Bang. Detecting primordial gravitational waves is one of the major goals of observational cosmology. The LIGO and Virgo detectors, which famously detected gravitational waves from colliding black holes and neutron stars, are sensitive to high-frequency gravitational waves from relatively recent cosmic events. But to detect the low-frequency gravitational waves from the early universe, we need different kinds of detectors. Future space-based observatories, like the proposed LISA mission, Laser Interferometer Space Antenna, might be able to detect these primordial waves. If we succeed, gravitational waves could give us a window into the inflationary era itself, potentially allowing us to test theories of what happened in the first 10 to the minus 35 seconds after the Big Bang. This would push our observational horizon back to a time so early that the universe was smaller than an atom, and conditions were so extreme that all the forces of nature might have been unified into a single force. The Hubble sphere, which we mentioned earlier, is another kind of horizon, sometimes called the photon horizon. Inside the Hubble sphere, Galaxies are receding slower than the speed of light relative to us. Outside the Hubble sphere, galaxies are receding faster than light. The boundary between these regions moves and changes depending on the expansion rate of the universe. In an accelerating universe like ours, the Hubble sphere actually grows with time, even as the event horizon remains roughly fixed. This means that regions of space that are currently outside the Hubble sphere, currently receding faster than light, will eventually enter the Hubble sphere and start receding slower than light. This allows light emitted from those regions to eventually reach us, even though the regions are currently receding superluminally. This might seem paradoxical, but it's a consequence of the particular way our universe's expansion is changing. The expansion rate is decreasing in absolute terms, fewer kilometers per second per megaparsec. Even though the expansion is accelerating, the scale factor is growing faster and faster. This allows the Hubble sphere to grow, bringing more distant regions into the subluminal receding category. Each of these horizons represents a different kind of boundary, a different limit on observation. The particle horizon limits what we have been able to see so far based on the finite age of the universe. The event horizon limits what we will ever be able to see in the future based on the accelerating expansion. The surface of last scattering limits how far back in time we can see using ordinary light. The neutrino horizon potentially extends earlier. The gravitational wave horizon might extend earlier still. Together, these horizons form a nested set of boundaries, each one marking a different kind of edge to the observable. Within the innermost boundaries, we have detailed information. As we move outward toward more distant horizons, our information becomes more limited, more indirect, and beyond all the horizons lies the great unknown, the universe that exists but that we cannot access, the reality that is forever beyond our ability to measure or confirm. Understanding these different horizons matters because they define the scope of empirical science when applied to cosmology. They tell us what questions we might be able to answer with observations, and what questions might forever remain in the realm of theory and speculation. They force us to distinguish between what is unknown temporarily beyond our knowledge but potentially discoverable, and what is unknowable, at least through direct observation. Wolfgang Rindler, whose work in the 1950 seconds helped clarify the concept of cosmological horizons, emphasized that these boundaries are not merely philosophical abstractions. They have physical consequences. They determine what regions of spacetime can causally influence each other. They define the structure of the observable universe and set limits on how that structure can evolve over time. Future observations, particularly using gravitational waves and potentially neutrinos, might allow us to push some of these horizons back, to see earlier into cosmic history, or to gather information from regions currently beyond our reach. But some horizons, particularly the event horizon created by accelerating expansion, are likely permanent. They represent fundamental limits, boundaries that no technology, no matter how advanced, will ever allow us to cross. This brings us to a deeper question. What does it mean that the universe has these limits? What should we make of the fact that observation itself has boundaries? There's something profoundly humbling about the cosmic horizons we've been exploring. They remind us that human knowledge, for all its impressive reach, operates within limits. No matter how much we learn, no matter how sophisticated our instruments become, there will always be parts of reality that remain beyond our grasp. This is not a temporary state of affairs. We're not talking about phenomena we can't observe yet, but might be able to observe in the future with better technology. The cosmic horizons represent permanent boundaries. The universe beyond our event horizon will never be accessible to observation, no matter how long we wait or how clever we become. The universe as it was before the surface of last scattering will never be directly visible using electromagnetic radiation. Some questions we can ask about the cosmos might simply not have answers we can empirically verify. This situation is unusual in the history of science. For most of science's existence, limits on observation were practical, not fundamental. We couldn't see microorganisms until we invented microscopes, but there was no law of nature preventing us from eventually seeing them. We couldn't detect radio waves from space until we built radio telescopes, but the waves were there, waiting to be discovered. The cosmic horizons are different. They're not challenges to overcome. They're features of the universe itself, consequences of relativity and expansion, and the finite speed of light. They tell us that there are things we cannot know, not because of any failure of human ingenuity, but because of the structure of space-time itself. This has philosophical implications. Throughout history, humans have wondered about the extent of reality. Ancient philosophers debated whether the universe was finite or infinite. For most of history, these questions remained purely philosophical. There was no way to gather empirical evidence one way or the other. Modern cosmology has made enormous progress. We know the observable universe has a finite size, about 93 billion light-years across. We have strong evidence that the universe had a beginning about 13.8 billion years ago, at least in the sense that all matter, energy, space, and time that we can observe originated in the Big Bang. We can measure the expansion rate, determine the geometry of space, calculate the density and composition of matter and energy. But the cosmic horizons remind us that our knowledge is inherently limited. We cannot observe most of the universe if it extends beyond our particle horizon. We cannot verify whether space is truly infinite or merely very large. We cannot test theories about the multiverse if other bubble universes are beyond our cosmic horizon. We cannot directly observe the earliest moments after the Big Bang if they occurred before the surface of last scattering. Some scientists find this frustrating. Paul Steinhardt, for instance, has argued that if inflation and the multiverse make our theories untestable, we should look for alternative theories that make testable predictions. The job of science, in this view, is to explain what we observe, not to postulate infinities of unobservable universes. Others take a different view. They point out that our best theories, quantum mechanics, general relativity, the standard model of particle physics, all have implications that extend beyond the directly observable. We can't observe an electron's wave function, only the results of measurements. We can't observe the interior of a black hole. We can't observe most of the fields and particles in the standard model without building enormous accelerators. Yet we consider these theories scientifically legitimate because they make testable predictions about what we can observe, even if parts of the theories refer to unobservable entities or regions. In this view, the multiverse isn't necessarily unscientific, even if we can't observe other universes. If the theory of eternal inflation makes testable predictions about the observable universe, about the patterns in the cosmic microwave background, for instance, or about the distribution of galaxies, then it's a legitimate scientific theory, even if it also implies the existence of unobservable regions. The debate gets at a fundamental question: what is the scope of scientific knowledge? Is science limited to what we can directly observe, or can it legitimately make claims about unobservable aspects of reality based on what we do observe? The cosmic horizons also raise questions about the nature of truth and knowledge. If there are infinitely many regions of space beyond our horizon, regions we can never observe or interact with, in what sense can we say we know they exist? We might have good theoretical reasons to think they exist. Our best models might predict they exist. This is the difference between what's unknown and what's unknowable. Much of the universe is currently unknown. We haven't observed it yet, or we haven't figured out how to interpret what we observe. But the unknown is potentially knowable. With more time, better instruments, or cleverer analysis, we might learn what we don't currently know. the unknowable is different. The universe beyond our event horizon is unknowable, at least through direct observation. The moments before the surface of last scattering are unknowable, using electromagnetic radiation. These aren't temporary gaps in our knowledge. They're permanent features of our epistemic situation, built into the structure of reality itself. Historically, humans have had to grapple with limits on knowledge before. In the ancient world, the edge of the known world was the limit of what explorers had traveled to. Beyond that edge lay terra incognita, unknown lands that might or might not exist. But those limits were temporary. Explorers eventually sailed across oceans, circumnavigated the globe, mapped every continent. The unknown became known. In the 20th century, physicists encountered different kinds of limits. Heisenberg's uncertainty principle in quantum mechanics says that certain pairs of properties like position and momentum cannot be simultaneously measured with arbitrary precision. It's a fundamental feature of nature. The more precisely you measure a particle's position, the less precisely you can know its momentum, and vice versa. Similarly, Gödel's incompleteness theorems in mathematics show that any sufficiently powerful formal system will contain true statements that cannot be proven within that system. There are mathematical truths that are forever unprovable, not because we haven't been clever enough, but because of the logical structure of mathematical systems themselves. The cosmic horizons represent a similar kind of fundamental limit, but applied to cosmology and observation. They tell us that there are aspects of the physical universe that are forever beyond our ability to empirically verify. This doesn't mean those aspects don't exist. The universe beyond our horizon is just as real as the universe within it. But it means our knowledge of those aspects must remain indirect, inferred from theory rather than confirmed by observation. Does this mean cosmology is no longer an empirical science when it makes claims about regions beyond the horizon? Not necessarily. The theories that predict what lies beyond the horizon are the same theories that successfully explain what we observe within it. If inflation explains the uniformity and flatness of the observable universe, and inflation also implies a much larger universe beyond what we observe, then we have indirect evidence for that larger universe. Not proof, but evidence. The situation is similar to how we understand the interior of the Earth. We can't directly observe the Earth's core. We can't drill down thousands of kilometers through solid rock and metal. But we can observe seismic waves from earthquakes, and from how those waves travel through the Earth, we can infer what the interior must be like. We have good reasons to believe the Earth has a solid inner core and a liquid outer core, even though we've never seen them directly. Similarly, we might have good reasons to believe the universe extends beyond our horizon, even though we can never see those distant regions directly. The reasons come from our theories, from the patterns we observe in the part of the universe we can see, from the way those patterns fit together into a coherent picture. But there's a difference. We could, in principle, drill down to the Earth's core if we had the technology. It would be extraordinarily difficult, perhaps impossible in practice, but there's no law of nature preventing it. The cosmic horizon is different. No technology, no matter how advanced, will allow us to observe beyond the event horizon. The limit is built into the structure of space-time. This means that some of our cosmological theories might forever remain in a state of being well supported but not definitively confirmed. We might have very good reasons to believe in a larger universe beyond our horizon, or in a multiverse of bubble universes, but we might never be able to move from very good reasons to empirical confirmation. For many scientists, this is uncomfortable. Science prides itself on testability, on the ability to confirm or refute theories through experiment and observation. A theory that makes predictions we can never test feels less scientific, even if the logic that leads to the theory is impeccable. But perhaps this discomfort is itself a sign of progress. For most of human history, We had no idea that there were limits on observation built into the structure of the universe. We thought, implicitly, that anything that exists can in principle be observed, given enough time and ingenuity. The discovery of cosmic horizons shows us that this assumption was wrong. Reality is larger and stranger than we imagined, and some of it will forever remain beyond our reach. This doesn't mean we should give up on observation or empirical science. Far from it. It means we should appreciate how much we can observe, how fortunate we are to live at a time and in a place where cosmic history is still accessible to study. And it means we should be humble about the limits of knowledge, recognizing that no matter how much we learn, there will always be more that we cannot know. It's easy, when contemplating cosmic horizons and the vast unknowable universe beyond them, to feel insignificant or even melancholy. We're confined to a tiny bubble, 93 billion light years across, which sounds large until you realize it might be an infinitesimally small fraction of the total cosmos. We can't reach most of what we can see. We're isolated, watching as the universe slowly erases itself from our view. But there's another way to look at it. The observable universe, for all that it might be a small fraction of the total, is still magnificently vast. It still contains wonders almost beyond comprehension. Our observable universe contains an estimated 2 trillion galaxies, according to recent calculations. Each galaxy contains tens of millions to hundreds of billions of stars. Each star is a sun, many larger and more luminous than our own. Around many of those stars orbit planets, worlds of rock or gas or ice, each one a unique environment shaped by billions of years of physics and chemistry. The sheer number is staggering. If there are 2 trillion galaxies, and each contains on average 100 billion stars, that's 200 sextillion stars, a 2 followed by 23 zeros. And around those stars might orbit quadrillions of planets, many of them in the habitable zones where liquid water could exist, where life might arise and evolve and perhaps develop intelligence and civilization. We live in a universe rich beyond imagination, and almost all of it is within our observable horizon. We can watch how they form and evolve, how they interact and merge, how they're distributed across cosmic space in vast filaments and sheets separated by enormous voids. The Hubble Space Telescope, particularly in its deep field observations, has shown us just how rich the observable universe is. In 1995, astronomers pointed Hubble at a small, apparently empty patch of sky in the constellation Ursa Major. They let the telescope stare at this patch for days, gathering every photon it could detect. The resulting image, called the Hubble Deep Field, showed not emptiness, but thousands of galaxies, stretching back in time nearly to the beginning of the universe. Every faint smudge in the image was an entire galaxy, containing billions of stars, seen as it was billions of years ago. The Hubble Ultra Deep Field, released in 2004, went even deeper, showing galaxies as they appeared when the universe was only a few percent of its current age. The James Webb Space Telescope, launched in 2021, has pushed even farther, detecting galaxies that formed within the first few 100 million years after the Big Bang. We are seeing cosmic dawn itself, the moment when the first stars ignited and the first galaxies assembled. And all of this, these deep fields revealing thousands of distant galaxies, these observations reaching back 13 billion years into cosmic history, all of this is within the observable universe. It's all accessible to us, at least in principle. We are not cut off from cosmic history. We live at a moment when the universe is still observable, when evidence for its origin and evolution is still within reach. This won't always be true. As we discussed earlier, the accelerating expansion of the universe means that distant galaxies will eventually recede beyond our event horizon. In the far future, observers in our local region we'll see only nearby galaxies. The cosmic microwave background will fade into undetectability. The evidence for the Big Bang will disappear. Those future observers, if they exist, will live in an empirically smaller universe than we do. But we live now. We live at a remarkable moment in cosmic history, a moment when observation is possible, when the universe reveals itself to those who look. Thousands of years ago, humans looked up at the night sky and wondered about the lights they saw. They began the long process of trying to understand the cosmos. And now, after millennia of observation and thought, after centuries of scientific revolution and technological innovation, after decades of space telescopes and particle accelerators and gravitational wave detectors, we can see back to nearly the beginning of time. We can observe galaxies billions of light years away. We can detect gravitational waves from colliding black holes. We can measure the temperature fluctuations in the cosmic microwave background and use them to determine the age, composition, and geometry of the universe. This is an extraordinary achievement. We live on a small planet orbiting an ordinary star in the outskirts of a typical galaxy, and yet we have managed to determine the basic structure and history of the entire observable cosmos. We have measured its age to a precision of about 1%. We have mapped its large-scale structure. We have traced the formation of galaxies and stars from the tiny density fluctuations in the early universe. And we're not done. The next generation of observatories will probe even deeper, see even farther, measure even more precisely. The Vera C. Rubin Observatory, which began observations in 2024, will survey the entire visible sky every few nights, creating a time-lapse movie of the cosmos that will reveal everything from nearby asteroids to the most distant quasars. The Square Kilometre Array, a radio telescope spread across multiple continents, will detect faint signals from the era when the first stars formed. The LISA space-based gravitational wave detector, planned for the 2030 seconds, might detect gravitational waves from the inflationary era itself. We are pushing at the boundaries, trying to see as much as we can while we can. And what we're learning is that the universe is even more interesting, even more surprising than we imagined. Dark matter and dark energy, the two dominant components of the cosmic energy budget, remain mysterious. We don't know what they are, only that they exist and that they shape the evolution of the cosmos. The earliest galaxies seen by James Webb appear to be more massive and more structured than we expected, challenging our models of how galaxies form. Gravitational waves have opened an entirely new window on the universe, allowing us to observe phenomena invisible to telescopes. Every answer we find seems to raise new questions. This is how science works, not by reaching final answers, but by progressively refining our understanding, by discovering that reality is more complex and surprising than our previous theories suggested. The cosmic horizons tell us that we'll never answer every question, but they don't diminish the value of the questions we can answer, the observations we can make, the understanding we can achieve. In a universe where observation is fundamentally limited, where most of reality might be forever beyond our reach, the fact that we can observe anything at all is remarkable. The fact that we can see 13 billion years into the past, detect galaxies trillions of times more distant than our own sun, measure the temperature of the universe when it was only 380,000 years old. These are extraordinary capabilities for creatures who evolved on one small world to make sense of their immediate environment. We are, in a sense, incredibly fortunate. We live in a galaxy old enough that heavy elements exist, that planets can form, that life can arise and evolve. We live in a universe that, despite its vastness and despite the limits on observation, is comprehensible. The cosmic microwave background is almost perfectly uniform. The light from distant galaxies carries information we can decode. None of this was guaranteed. We might have lived in a universe where observation was impossible, where the laws of physics were so chaotic or complex that no intelligence could understand them. Instead, we live in a universe that's large enough to be interesting, old enough to have evolved complex structure, and regular enough to be comprehensible. The observable universe is a gift. It's a realm we can explore, study, and marvel at. And while it might be a tiny fraction of the total cosmos, it's still vast beyond our ability to fully explore it, rich beyond our ability to fully catalog it, mysterious enough to keep us wondering and investigating for as long as our civilization endures. We've traveled together to the edge of the observable universe, and we've encountered multiple boundaries, the particle horizon marking how far light could have traveled in the age of the cosmos, the surface of last scattering representing the oldest light we can see, the event horizon defining what we could ever see in the future, no matter how long we wait, and the theoretical speculations about what might lie beyond it all. These horizons are nested like Russian dolls, each one revealing a different limit, a different kind of boundary between the known and the unknown. The surface of last scattering sits at about 46 billion light-years, marking the practical limit of electromagnetic observation. The particle horizon stretches to the same distance, defining the edge of our past light cone, the boundary of what could have causally influenced us. The event horizon lies closer, at about 16 billion light-years, marking the terrible asymmetry where we can see farther than we can reach, where past is accessible, but future is not. And beyond all these horizons, beyond even the theoretical speculations about inflation and multiverses, lies the fundamental mystery. The universe extends beyond what we can observe. How far beyond? We don't know. Perhaps infinitely far, perhaps just a little farther. We cannot say with certainty, and we might never be able to say. This situation, living inside an island of observable space, surrounded by an ocean of the unknowable, is simply the nature of our existence as observers in this universe. It's not something future technology will overcome. It's a feature of reality itself, a consequence of the finite speed of light, the expansion of space, and the finite age of the cosmos. But here's what I find beautiful about this. The limits don't diminish the wonder. They enhance it. If we could see everything, if there were no horizons, no boundaries, no unknowable regions, would the universe be more or less interesting? I think it would be less. The fact that there's more beyond what we can see, the fact that reality extends farther than we can reach, the fact that some questions might not have answers, we can verify all of this, adds to the richness and depth of existence. Mystery is not a bug in the universe. It's a feature. It's a reminder that reality is larger than our comprehension of it, that no matter how much we learn, there's always more to discover, more to wonder about, more to imagine. The horizons tell us that the cosmos is not a small, comprehensible place that humans can fully map and understand. It's vast, possibly infinite, filled with regions we'll never observe and phenomena we'll never detect. And yet, within our cosmic island, we can do so much. We can observe galaxies billions of light years away. We can detect the faint glow of the Big Bang. We can measure the expansion rate of the universe and determine its age and composition. We can predict, at least in broad strokes, what will happen in the future, how galaxies will evolve, how the expansion will continue, how the universe might end. The fact that we've learned this much, starting from our small planet orbiting an ordinary star, is remarkable. Ancient humans looked up at the stars and wondered. Modern humans look up with telescopes and satellites and gravitational wave detectors, and we've answered many of those ancient questions. The stars are suns. The Milky Way is a galaxy. The universe had a beginning. Space itself is expanding. These are answers to questions humans have asked for thousands of years, but the answers have led to new questions, deeper questions, questions that might not have answers we can empirically verify. What came before the Big Bang? What lies beyond our cosmic horizon? Is the multiverse real? Are there other universes with different laws of physics? Is our universe finite or infinite? These questions push at the boundaries of science. Some of them might forever remain partially answered, where we have good theoretical reasons to believe something but can never definitively confirm it through observation. This is uncomfortable for a scientific culture that values testability and empirical verification above all else. But it might be the reality of doing cosmology that some questions take us to the edge of the empirically knowable. And maybe that's okay. Maybe the value of cosmology isn't just in the answers we can confirm, but in the questions we can ask, in the framework we can build for thinking about the universe, in the sense of wonder and perspective we gain from contemplating our place in the cosmos. The cosmic horizons teach us humility. They teach us that human knowledge, for all its power and reach, operates within limits. They teach us the difference between what's unknown and what's unknowable, between temporary ignorance and permanent mystery. They remind us that the universe doesn't owe us answers, that reality is not obligated to be comprehensible or observable. But they also teach us gratitude. We are fortunate to live in a universe that's observable at all, that follows regular laws we can discover, that leaves evidence of its history we can detect and analyze. We're fortunate to live at a time when that evidence is still accessible, before the accelerating expansion has erased the cosmic microwave background and carried distant galaxies beyond the horizon. We're fortunate to have developed the science and technology to make these observations, to have built a civilization capable of looking outward and asking fundamental questions about existence. When you look up at the night sky now, you can think about the invisible boundaries that surround what you're seeing. You can think about the light that's traveled billions of years to reach your eyes, crossing space that was expanding the whole time. You can think about the galaxies you can see that are now receding beyond reach, their futures forever inaccessible. You can think about the vast universe that might exist beyond what you can observe, regions of space that are just as real as what you see but forever beyond your horizon. And you can appreciate the mystery of it all. The fact that there's more we don't know than what we do know. The fact that the cosmos is vast and strange and full of wonders we're only beginning to understand. The fact that observation itself has limits, but those limits don't prevent us from observing enough to be amazed. We live inside a bubble of observation, an island of light in an ocean of darkness. What stories it tells us about where we came from, how we got here, and what might lie ahead. The universe has drawn its horizons around us, but within those horizons lies enough to occupy human curiosity and wonder for as long as our species endures. And beyond those horizons, well, there lies the mystery, the great unknown, the possibly unknowable. And there's a strange peace in accepting that some things might always remain unknown. Not the peace of giving up or stopping inquiry, but the peace of recognizing that mystery is woven into the fabric of existence, that we live in a universe larger and stranger than we can fully comprehend, and that this is not a deficiency but a gift. If this journey through cosmic horizons has resonated with you, if you've found something valuable in exploring the limits of observation and what they mean for human knowledge, I'd be deeply grateful if you'd consider liking this video and subscribing to the channel. Your support helps me create more content like this, more explorations of the profound questions at the intersection of science, philosophy, and wonder. There's so much more to explore together: the nature of time, the mysteries of consciousness, the structure of reality itself. I'd love to have you along for those journeys. Thank you for traveling with me to the edge of the observable universe. Thank you for contemplating these boundaries with me, for wondering about what lies beyond, for appreciating both what we can know and what must remain mystery. Look up at the stars tonight, if you can. Look up and remember that everything you see exists within an invisible sphere, a cosmic horizon that defines the limits of human observation. And remember too that beyond that horizon lies more universe, possibly infinitely more, forever beyond our reach, but no less real for being unobservable. The cosmos is vast. The horizons are real. The mystery endures. And somehow, in all of that vastness and mystery, here we are conscious beings, capable of wondering, capable of reaching out across billions of light years to touch the edge of the knowable universe. What a privilege it is to wonder. What a gift it is to observe. What a strange and beautiful thing it is to be aware, in this moment, of the limits of what we can know and the infinite reach of what we can imagine beyond those limits. Sleep well under your cosmic horizon. Dream of the infinite beyond, and wake tomorrow ready to wonder again